All right, let's go ahead and get started. Welcome. We're so excited to have our first set of lightning talks for the semester. We are excited to be getting into 2022 and hopefully making it a better year than 2021. We'll hopefully have our in-person conference this year, which is going to be even more exciting. But we are going to continue our 2021-2022 online conference right now. So we have 4 amazing presenters today. I am not sure if we have an order in mind or if anyone wants to volunteer to go first, but we can go ahead and get started.
I'm happy to go first if no one else wants to.
Great. I love the intention and activism behind that.
Okay.
Floor is yours.
Let me share my screen. Can anyone see my screen? Can anyone hear me? Okay, I'll get started then. Thank you for coming. So today I'd like to talk about affordances of fractions and decimals for arithmetics. Now we know that rational numbers can be presented in different formats. For example, we can present a number as a fraction, like 1/4. That same number can be presented as a decimal as well, like 0.25. It can even be presented as a percentage, like 25%. So previous studies have found that different notations were preferred to present different information. Fractions were preferred to present information about concrete sets, while decimals and percentages were preferred to present continuous properties. In the current study, we are interested in investigating this affordance of notations in terms of arithmetics. Our main hypothesis is that decimals will afford addition better than fractions do, and fractions will afford multiplication better than decimals do. So we think that cross-notation conversion actually could reveal notation preference. So consider, let's say you prefer decimals for addition problems, but you are given a fraction addition problem. What you could do is you could actually convert the fraction into decimal and then solve the problem using the notation you prefer. Similarly, let's say that you prefer multiplication for fraction. Sorry, you prefer to use fraction for multiplication problems, but you were given a decimal multiplication problem. You could also convert that decimal into a fraction in order to solve the multiplication problem in the notation you prefer. Hence, we look at this cross-notation conversion rate. So our 2 main prediction is that first, we see that addition problems will be converted from fractions to decimals more and vice versa, whereas multiplication problems will be converted from decimals to fractions more than vice versa. Additionally, we think that on comparable fraction and decimal arithmetic problems, addition accuracy will be higher with decimals than fractions, whereas multiplication accuracy will be higher with fractions than decimals. So we conducted 2 studies. The first experiment had 70 participants. The second one had 80 participants. We did it with undergraduate population. Now let's take a look at the result. First, looking at the cross-notation conversion rate, on the y-axis, we have the cross-notation conversion rate. The yellow bar represents the fraction to decimal conversion, and the black bar represents the decimal to fraction conversion. So as we can see across both studies, for addition problem, the fraction to decimal conversion rate is higher compared to the decimal to fraction conversion rate. And for multiplication, we see that decimal to fraction conversion rate is higher than fraction to decimal conversion rate. So this suggests that for addition problems, it appears that our participants actually preferred decimal, and for multiplication, they actually seem to prefer fraction to solve it. Now, the accuracy pattern the accuracy reveals a similar pattern. So on the y-axis, we have the accuracy, and the yellow bar represents the fraction problems, and the black bar represents the decimal problems. As you can see again here, for addition problems, decimal addition accuracy is higher compared to fraction addition accuracy, where fraction multiplication accuracy is higher compared to decimal multiplication accuracy. So in conclusion, our hypothesis is supported. So we see that participants preferred decimal for addition, and their accuracy is also higher on decimal addition problems, and they preferred fraction for multiplication, and their accuracy is also higher on fraction multiplication problems. So we conclude that decimals affords addition better, and fractions affords multiplication better. So that's all I have for today. Do you have any questions?
I can start. So wonderful presentation. Thank you so much. And it's very interesting and very exciting finding. I think one thing that just popped into my head is thinking more developmentally, like because your population is undergrads. I'm wondering when this awareness or preference developed and what would be your hypothesis?
Thank you. That's a great question. Actually, we are currently planning to run a study in 6th to 8th graders when it's about the time for them to, to learn fractions and decimals and arithmetics. As to when does this adaptivity start, that's a even greater question. I would think that once they learned, both fraction and decimal addition and multiplication problems, and potentially a little bit after that, when they start to realize that, fraction addition actually is easier to solve compared to, decimal addition is actually easier to solve than fraction addition, and, fraction multiplication is actually easier than decimal multiplication. I would think that at that point, they would start to realize that it's actually beneficial to use one notation to solve a certain operation. So yeah, thank you. That was a great question.
I have a question.
Yes.
I would like, I would like to go even to younger people. Okay. And I'm thinking in 6, 7 years old children.
Okay.
And for instance, I think if you say one of these children, you have to add half and a half, it would be easier than probably saying, try to add a 0.5 and 0.5. I think it depends also in the fractions or in the correspondence between the meaning. Half is easy to understand, but 3/4 is more complicated maybe. And so I think that's also a variable that it's important. So I would like to know your opinion.
Definitely. I realized I forgot to include that exact graph. I apologize. So I think the main reason we think that fraction addition is in general harder than decimal addition is that, so consider adding two fractions of different denominators. Let's say half plus 1/3. First, we need to convert the two fractions into same notation, same denominator. So you need to convert the half into, say, 3/6. You need to convert the 1/3 into, say, 2/6, and then you can add them together. So procedurally, to add fraction between different denominator, you would need to first do a multiplication by converting both fraction into common denominators, and then you need to do addition. But for decimal addition, you don't need the extra step of multiplication. You can just straight up add the decimals. Now, similarly, when it comes to multiplication, so for fraction multiplication, you can just multiply the numerator, multiply the denominator, and then you're done. But for decimal, so long as you're not adding decimal with a whole number, you would you would need to add the decimal as if you're adding whole number. You would need to multiply the decimal as if you're multiplying whole number, and then you need to count the decimal places in both decimal points, and then add them together, and then you put it into the answer. So that requires multiplication and addition. So procedurally, that is also more complex. So we actually looked at, I apologize, I forgot to include that graph here, but we actually look at the cross notation conversion rate across different operands. And we found exact pattern such that cross notation conversion rate between fraction and decimal difference is the smallest when it's between a fraction of equal denominator or a decimal of equal decimal digit addition problems. And for multiplication, you see that the cross notation conversion rate difference is smallest when you are adding a decimal with a whole number, or when you're multiplying decimal with a whole number, or multiplying fraction with a whole number. So it kind of suggests that, you know, to go back, our main hypothesis is part of the explanation for our main hypothesis is that fraction multiplication is procedurally less complex than decimal multiplication, and decimal addition is procedurally less complex than fraction addition. And so there are certain cases, for example, when you're adding fraction with equal denominator, or when you're multiplying decimal with a whole number, where the procedural may not be more complex compared to the other notation, but in general, it is the case. And so thank you, that was a great insight. Yeah, sorry, I fluttered it.
All right, fantastic. I think it's time to move on to our next presenter. Thanks for that fantastic presentation. Does anyone want to volunteer to go next?
I can go next.
Awesome.
1 second. Let me share my screen. Does everyone see my screen and hear me okay? Sounds good? Okay. So hi everyone, my name is Ngo and I'm a master's student at Worcester Polytechnic Institute. And today I'm sharing my and my team's research, which looks into how superfluous brackets can support student performance during problem solving. So there's growing evidence that younger students often have weak structure sense, which is the ability to grasp arithmetic structures. And because of this, when solving math problems, students tend to neglect the structure of the problems, and instead they tend to jump right into calculation and doing so from left to right. And as you can see here, that strategy can lead students to solve problems inaccurately. So how can we support students during their problem solving? Grounded in perceptual learning theory, we look into how visual features and math expressions can support students' performance during their problem solving and potentially improve their structure sense. And from previous work, we know that visual features act as perceptual cues to influence how we act on math notation. For example, previous studies show that students solve problems more quickly and more accurately when the spacing in notation supports the order of operations than when it does not. So in our study here, we examine if superfluous brackets can act as a perceptual cue to support student performance. Superfluous brackets, also called superfluous parentheses in the US, are not necessary for problem solving, but they are there more for emphasizing the structure of the math problem. Similarly, we're also curious about whether position of higher order operand, so multiplications or division signs, and how the position of these signs within a math expression affect students' performance. While we know that students tend to solve problems from left to right, it is unclear how different locations of these operands affect students' performance differently, with and without the presence and support of superfluous brackets. And to answer our research questions, our team designed a 3x2 between subject study, which structure is shown here in details. 291 5th to 7th grade students completed a 3-item pretest, and then they were randomly assigned to one of these 6 conditions, where they solve order of operations problems that were presented differently based on their assigned condition. And this study was created as a problem set in Assessment, which is an online tutoring system. And we use mastery speed information from this system as an outcome variable for students' performance. So in this activity, students solve order of operations problem until they achieve mastery, which is defined as correctly answering 3 questions in a row. So in this example right here, the students got 2 questions right already, and they will have reached mastery if they get this 3rd question right. However, if they get this question wrong, they will see more problems and solve them until they get 3 more questions right in a row. And here we're interested in students' mastery speed as an outcome variable, as in how many problems did students solve before they solve 3 problems correctly in a row. And lower mastery speed should indicate higher performance and vice versa. We expect students solving problems with superfluous brackets to have faster mastery speed than students solving problems without. We also expect students solving problems with higher order operand to the left to have faster mastery speed than students in the center and right conditions. So from our current analysis, we found statistically significant differences in mastery speed between 2 pairs of conditions. First, we found that on average, students solve fewer problems and reach mastery faster when they solve problem with the higher order operand to the left than to the right, without the support of superfluous brackets. This finding supports the current observation that students have a strong tendency to solve problems from left to right. We also found that on average, students who solve problems with superfluous brackets and with the higher order operand in the center reach mastery faster than students who solve problems without brackets and with the operand to the right. This finding is a bit harder and trickier to interpret, but it's interesting nonetheless. And moving forward, we're going to run more analyses to tease out the separate effects of superfluous brackets and higher order operand on students' performance separately. Overall, this study adds to the current research on superfluous brackets as a perceptual cue to support students' performance. These findings also have implication on how educators can present learning materials in ways that support and optimize their students' performances and understanding of math. We found that students solve problems better when the higher operand is to the left than when it is to the right, which shows that students tend to solve problems from left to right. And by understanding this strong tendency, educators can think of easy and accessible ways that we can help, that we can do to help support students when they learn or when they struggle during problem solving. And that concludes my talk. I'd like to thank my team and my research lab for their support. Please feel free to reach out to me with any questions or feedback. Thank you for your time. Yeah, any questions?
I have a question for you. Thanks for your talk. It was great. Do you know from, you know, we are doing better from right to left. What happened with languages that are read from right to left, or left, sorry, yeah, right to left, and what happened with this? Do you know if there's some research on that?
Yeah, that's a really interesting question. So interestingly, so in we read when we were doing lit review for this project, I came across a study that was conducted in Japan, and for Japanese people, they read right to left sometimes in some contexts, and then left to left to right in others. So it was really interesting. But for that study, they found that students like solve problems, still have like a strong tendency to solve problem left to right. I guess it's just like because how they were introduced math when they were young. That's how when it comes to math is left to right. And also like in their normal days today, their reading still go left to right most of the time. But I would love to see more research being done in this area. And if you know of any research being done in like communities and like participants who read right to left, I was like, I would really appreciate having that, like knowing that information. It's really interesting. Thank you. So yeah, so if anyone has any more feedback or have any more questions, please feel free to reach out to us in these email and Twitter below. Yeah, thank you so much for your time.
Great, thank you. And I think if anyone has further questions, they can also ask them in the chat. I know several of the co-authors are here as well. All right, Colleen, Javier, would one of you like to go next? Great, Colleen.
Okay, can everyone hear me? Yes, okay, I'm gonna share my screen. Oops, I have the wrong thing open. All right. Okay, so today I'm gonna be asking the questions, do adults understand fraction addition? In terms of fraction learning in this country, in the US, schools devote significant attention to fraction instruction. Children are partitioning circles and rectangles into fractions starting in grade 1. They're representing them on a number line in grade 3, and they're learning to add and subtract fractions in grades 4 and 5. But despite years of schooling, many children and even adults struggle with fraction arithmetic. Braithwaite, Pike, and Siegler, 2017, in that paper, they hypothesized that children struggle to learn fraction arithmetic because their learning develops without conceptual understanding. So in a previous study, Braithwaite, Tan, and Siegler tested this hypothesis with 6th and 7th graders. In their experiment, they had children estimate individual fractions and sums on a 0 to 1 number line, estimate individual whole numbers and sums on a 0 to 1,000 number line. And for the sums, children were instructed not to calculate exact answers, but instead to estimate by imagining adding the sizes of the two numbers together. Based on their results, we were curious how adults would fare on the same items, and that led us to our current study. But first, I'm just going to review the previous study. In Braithwaite, Tan, and Siegler, they used PAE to estimate, to calculate estimation accuracy, and PAE, percent absolute error, is found by taking the absolute value of the difference between the participant's estimate and the correct response, and then dividing that by the range. And because of that, higher PAEs indicate less accuracy. Their PAEs diverge from normal distributions. They analyzed them using linear and mixed models and bootstrapping, and we did the same in our study. So these are the, in their study, they found for the children, the 6th and 7th graders, that number type, which whether it was a fraction or a whole number, interacted with estimation tasks, whether they were estimating an individual number or a sum. And they found that the discrepancy between children's estimates of whole number sums and individual whole numbers, there was a much smaller discrepancy for the whole numbers than there was for the fractions. There was quite a large discrepancy between children's ability to estimate individual fractions and fraction sums. They also looked at the direction of effects principle. And this principle says that as a basic principle of addition, sum of two positive numbers is at least as large as either addend. So if I'm adding 1 plus 2, I know that the sum is going to be greater than 2. If I'm adding 1/8 plus 3/5, I should know that the sum will be greater than either 1/8 or 3/5. And to determine if the children violated this principle or not, they used a pretty lenient standard. They basically said, okay, we're not going to look at whether your estimate of 1/8 plus 3/5 was greater than 0.6. We're going to look at whether it's greater than wherever you thought 3/5 was on the number line. So if a child estimated 1/8 here and 3/5 here, even though this is not accurate, it should be over here, they were found not to have violated the direction of effects principle if their estimate of 1/8 plus 3/5 was over here, greater than whatever their estimate of 3/5 was. Despite that very lenient criterion, in the original study, children's estimates violated the direction of effects principle in about 52%, more than half of the trials for the fraction sums, but only 15% for the whole number sums. So in our current study, we use the same study materials and the same study items and a new sample. Our sample was adult undergraduates attending elementary education programs in public universities in New York and Ohio. We chose pre-service teachers because they will have received all the rational number instruction typical of US students because they're in college, and because they will be responsible for teaching children about fractions. in the future. So we were curious how they would do. We tried 2 types of number lines, which was not from the original experiment. We wanted to see if plotting a point on a number line would differ from dragging a bar to sort of show a length as a magnitude. Basically, we found out that our number line condition didn't matter, so I'm not gonna talk about that more, I just wanted to mention it. And our results, we also found the same interaction between type of number, whether it was a fraction or a whole number, and estimation task, whether they were estimating an individual number or a sum. And similarly, the adults, did better on the fraction sum estimation, but there was still a very large discrepancy between estimating a fraction sum and estimating an individual fraction, but not much between the whole number sums and the whole numbers. So comparing our results to the original study's results, we find that for individual whole numbers and for whole number sums, it was pretty similar. The adults and sixth and seventh graders did very similarly, and both groups did similar, they were similarly accurate estimating individual whole numbers as they were estimating whole number sums. However, when we look at the fraction sums, their estimates
Seems we've lost audio. Is anyone else getting that?
I think, Colleen, you're muted.
Yes, it seems you accidentally muted yourself.
Sorry, can you hear me now?
We can hear you now. Yep.
Okay, I'm sorry. I was just trying to move the box so I could see my screen. So where was I? What was I talking about when I got cut off? I'm sorry.
You just started this page.
Okay. So for so what I would point out is that the results for both the middle schoolers and the adults were similar for the whole numbers. There's not a huge discrepancy between their ability to estimate whole number sums and estimate individual whole numbers, but for fraction sums, there's quite a large discrepancy between the accuracy when estimating fraction sums, which is very inaccurate, and estimating individual fractions, which is much more accurate. And so based on this, we would say, we can't really say that either the adults or the children had difficulty estimating fraction sums because they don't understand what it means to estimate a sum, because they actually did quite well for the whole number sums. We also can't say that the difficulty estimating fraction sums is because they don't understand the magnitudes of individual fractions, because again, they, there is evidence that they do understand the magnitudes of the individual fractions better. In terms of the direction of effects principle, as with the previous study, we found that for whole number sums, there weren't that many violations, but for fraction sums, it wasn't as prevalent that the adults violated this principle, but they violated it 42% of the time instead of 52% of the time, basically. Another finding we had when we looked at our data, we looked at the mean PAE estimates for each type of task. And we found that we noticed that there's a difference between how the mean estimates trend for fraction sums than for the other types. And basically they seem to be showing a pronounced underestimation trend, and we weren't really sure why that was. We hypothesized that maybe even though we asked participants to actually think about the sizes of the numbers and add them together, that some of them might be relying on an incorrect add across strategy where they're adding the numerators and the denominators, and that might explain why 3/5 plus 1/8, for example, you'd get an answer closer to 0.3. Because of students, these purple X's show the values you would get if you add across, and these black X's show the actual values. So you could see how if some participants were applying this add across strategy and some were trying to use more of a magnitude-based strategy, it might result in a trend like this. So in study 2, we're going to be asking participants to explain their answers and hopefully finding out a little bit more about what participants are trying to do. So in conclusion, I just want to thank members of our lab who helped me with data entry. I also want to thank David Braithwaite and Jing Qian, the authors on the previous paper, the 2018 paper, because they shared their data and answered our questions. So thank you to them. And that is all. So I will take questions if anyone has questions.
Well, I think I have a question again.
Okay.
And and congratulations. Okay, it was really, really interesting. I don't know if it will help to have a condition with the same denominator in the fractions. So this way, this will be more similar to numbers, to natural numbers. Okay, and well, and that's my point. Okay, thank you.
So you're suggesting, just to understand, having some conditions where they're adding fractions with the same denominator. So like 1/5 plus 2/5, for example.
Yeah, my point is that when you are adding fractions with different denominators, then you are adding some error because you are not so precise. So you are adding two errors. And you have the same denominator. Okay, it's the easiest thing you can imagine, and that should be really similar to the other thing. But then you know more about why you find this different. Okay.
It's an interesting idea. Yeah, I mean, in that case, I guess when they were even if, I guess my concern would be if we did that they really would just calculate the answer. But I also see that in terms of an estimate, that could be very interesting because they would kind of iterate the same denominator. So yeah, thank you for that suggestion. I will consider that for study too, for sure. Okay, and Alexandria is asking if we know if adults have a similarly hard time estimating decimal sums on a number line. I don't know the answer to that. Unfortunately, we haven't looked at decimals at all in our studies. I don't know if anyone else has knowledge of that.
If I'm not mistaken, although it's been a while, I believe study 3 of Ken et al. That you cited has a decimal estimation task, although it's not on a number line. It's numerical estimation of decimals, and they were quite accurate with decimals compared to fractions. I don't know if it's the same on a number line though.
Thank you, David. Yeah, that was experiment 3. But again, as David pointed out, it wasn't on a number line.
If I may ask a question, a great talk. And I'm curious if you have any just preliminary impressions about how the participants are doing the task. You suggested that in the second study, you're going to ask systematically for explanations. I wonder if you, just from talking to participants or hearing them mumble things, do you have any preliminary impressions? I guess what's behind the question is that estimation is really kind of a negative instruction. Like when we tell someone to estimate, we're not telling them what to do, but really what not to do. We're saying don't calculate, but as for what they actually do in order to determine where to put their mark, it's somewhat of a mystery. So do you have any impressions from the participants or any other source?
Yeah, so we've started collecting data with both middle school students and adults. And we're collecting the data in 2 ways. One is that we are asking them for 8 of the fraction sums, we're asking them to, we didn't do it with whole number sums, we only did with fractions. And we asked them to explain how they found their answer for 8 of the 16. And what we found is that some participants are really describing what we asked them to do. They're saying, I thought about how big 3/5 was and how big 1/8 was, or I thought about how big 3/5 was and I put 1/8 a little bit further to the right on the number line. And then there are other students who are saying things like that they added across. Some students simply write the value of the add across, the answer you would get if you added across, which is incorrect. And a few students seem to be using an averaging strategy where they're reasoning in their head, well, 3/5 is more than a half, 1/8 is less than a half. So the answer is going to be a little less than a half. And I don't really understand why they're averaging, given that we're asking them to add. But there is a minority of participants who seem to be doing that. So I'm definitely interested in that. I'm interested in the students who are adding across as well, because I think that, you know, they're relying on an incorrect procedure. And if they had some more conceptual understanding, maybe they wouldn't be doing that.
Yeah, that's really interesting. I don't know if you've sort of sit down and written the calculations out, but if you do the adding across strategy, you actually got an answer that is pretty close to averaging.
Yes.
Although the students probably don't know that. So it might be very hard to distinguish those two strategies based on the answers they give, but they could be maybe distinguished based on the feedback from participants. Thank you.
Yeah, based on the explanations, we can do that, but you're right. The averaging strategy and the add across strategy, it's almost exactly identical. It's very, very similar values you get. And also, I don't think the students who are averaging are actually averaging the values. They're just kind of doing like a rough average in their head. So we're also going to be analyzing our data using Bayes factor analysis. So for that, we're just going to collapse the add across and averaging into one incorrect strategy category, because you're right, numerically, there's no way to parse that out, but hopefully we can parse that out a little bit by looking at how they explain their answers. And then of course, there's also the students who don't seem to be using any strategy at all, who just kind of, the data is kind of random and I'm not really sure what they're doing.
All right, any other questions we can drop in the chat and Colleen can answer those for us. Javier, we have our last presentation now.
Okay. Sorry, so many things open here. Now, can you see the presentation? Yeah, okay. So this research is focused on multi-digit number comparison, and it has been debated if this is a decomposed process or if we build a holistic representation of the numbers. And it has been also debated if we do this comparison following a parallel process or a serial process. Here, the unit decade compatibility effect has shed some light, suggesting that we use a decomposed and parallel procedure when we compare multi-digit numbers. This effect shows that we take into account units even although they are not relevant for the task. So in the example, we can see we don't need information about the units to take a decision, but when the unit is in the bigger number is smaller than the unit in the large number, we found larger reaction times. Okay. So the conclusion from the compatibility effect is that people seems to analyze several properties of the multi-digits in parallel to do the comparison task. And an important thing is the compatibility effect is context sensitive. This means that if we include in the experimental set more items that have the same digit in the decade place, then you focus the attention of participants in the units, and then in these cases, the compatibility effect increases. Huber and colleagues have proposed a computational model to explain the comparison of multi-digits, and they have layers for the comparison of hundreds, tens, units, for the comparison of different numbers that could be positive or negative. And what is relevant for the research I'm going to present is they also include a layer for comparing numbers that has different number of digits. So for instance, if we are going to compare 3 against 4, a number with 3 digits with a number with 2 digits, okay? On top of this, they put a cognitive control network that would be responsible of being sensitive to context, okay? Well, so our research is the first research trying to explore what happens when we are comparing multi-digit numbers that differ in the number of digits. According to Huber model, we will use many different types of information. So we can use the number of digits, and this is the more relevant information. But as we are processing different attributes of the multi-digits, the information about the leftmost digits could be also relevant according to the model. An alternative position is that as length, number length, in the length in number of digits is so salient, so relevant, it is possible that people decide only taking into account the number of digits and not paying attention to the digits value, the value of the leftmost digits. So our question is when comparing numbers of different length, people would rely only in length, or they would pay attention to the leftmost digits identity. And we would like to know if they pay attention to the leftmost digit, it would be related with the nature of the characteristics of the experimental set. So we created congruent pairs and incongruent pairs. Incongruent pairs, we have numbers with 4 digits, and these numbers start with a digit that is larger than the number in the 3-digit number. On the contrary, in the incongruent pairs, we have 4 and 3-digit length numbers, but in this case, the leftmost digit of the 4-digit number is smaller than the leftmost digit of the 3-digit number. Okay. Well, we also manipulate the number of same length pairs in the blocks. So we have a condition with 25% of same length items, another condition with 50%, and another condition with 75%. Okay. They have simply to decide which number was bigger, pressing the K of the corresponding side. And here we have the results of 2 experiments. The difference between experiment 1 and 2 is that in experiment 1, the filler blocks were run in different sessions, whereas in experiment 2, the experiment was run in a single session. You can see the results are pretty similar, and we found a congruity effect showing faster response times in congruent items. And we did not find an interactions between congruity and filler ratio. This means that the effect of congruity was not sensitive to the experimental list. We collected pulled together the data from experiment 1 and 2 to see if we can get more power, and if in this case we found the interactions between congruity and filler ratio, and again we failed to find this effect. Okay, so the finding of the congruity effect indicates that although participants are reaching a decision based on length, the leftmost digit is also processed and affect the speed of this decision. Regarding the cognitive control mechanism, it seems that it was not sensitive. It was not sensitive to affect the congruity effect. It's like the focus in the leftmost digit was not affected by the item set. Okay, so we ran a third experiment, and in this case we extreme the manipulation. So we use 50% of same and different length numbers against a condition where we have no same pairs, same length pairs. So they were all in this condition 3 against 4-digit length numbers. And we also manipulate the distance between the leftmost digits. So in the previous study, we only use a distance of 1. And now we use also a distance of 4 that should increase the congruity effect, as it would be more evident the difference between one number and the other because the distance is bigger. So, and these are the results. In the pure condition, we found no congruity effects, and we find a 25 milliseconds congruity effect in the mixed condition. So when there are no same pairs in the experimental set, the congruity effect disappears. So we find the interaction, and interestingly, we don't find effects of distance. So they are not included in the figure. Okay. So to conclude, the congruity effect indicates that both length and the leftmost digits are taken into account, but the absence of distance effects suggests that when we are analyzing the leftmost digit numbers, we did not compute the distance between them. Probably we are doing a superficial analysis, considering this is big and this is small, but we are not processing exactly the distance between them. Regarding the second question, is the cognitive control mechanism sensitive to the proportion of same different length numbers? Now we can say yes, but only if we extreme the manipulation. So we had to compare 0 against 50% to find that difference. So if the model can explain this data, and I want to finish with a question for the future. What is exactly processing number length? We are saying the participants are comparing numbers with 4 numbers against numbers with 4 digits against numbers with 3 digits. And we don't know exactly if they compute the exact number of each string, or if they are using a perceptual shortcut or cue to decide, okay, this is bigger, occupies more space, and then should be the biggest number. And we have a response for this in experiments we are currently running, and I hope we will have a response to this in the next meeting of the society in Antwerp. Okay, thank you.
All right, do we have any questions for Javier, or we're really excited to see the follow-up on this in about 5 months now? Yes, love the cliffhanger, love the invitation to come to Belgium. All right, an excellent description. No questions needed. Thank you all so much for being here this morning or afternoon. Thanks for taking your Friday afternoon, Javier, to hang out with us. We are looking forward to further presentations, and our next MCLS meeting will be next Thursday morning at 9 a.m. Eastern, and we will look forward to seeing you all there. Thank you so much. Have a great weekend.